All right, hey folks, how we doing? Continuing along with this kinetics. So we're gonna get into what I think is some really cool stuff. I think I'm probably saying that at the beginning of every single one of these videos. So I'm gonna get into, on this lecture, pseudo first order reactions, which I'll describe here momentarily. And I think I should have enough time to also talk about equilibrium, as well as temperature based reactions. So reactions affected by temperature. So I'm going to keep my eye on the time, and we'll see how many of these slides I can get through. Okay. So a pseudo first order reaction are really interesting, and this is really practical for how kinetics is actually done in the laboratory. So pseudo means kind of, in the simplest way. So it's kind of a first order reaction, okay? And so what makes this a pseudo first order reaction, I need plenty of room on the slide. So I'm going to start up here, and I'm going to say, suppose that we have a second order reaction, okay? So suppose we have a reaction that's first order in A and first order in B, giving us a true second order reaction. As it turns out, these reactions are pretty difficult to do experimentally, because you'd have to monitor the concentration of both A and B simultaneously. And that can be done. It's not impossible. However, it's difficult. So we can make this what's called a pseudo first order reaction by imposing the following. We can make the initial concentration of B much greater than the initial concentration of A, or provide a steady source of B such that the following. So in either one of these, we either make the initial concentration of B much larger than the initial concentration of A. If that's not feasible, if that's not something we can actually do, then in our reaction we can continually add B. And we can continually add B at a steady rate such that the concentration of B at any time is always roughly equal to the initial concentration. So either scenario gives us this notion that B is not going to change in time. Okay? So if B is much greater than A, if B reacts away, it doesn't really look like much changed. Or, and this is what I think is more realistic, we're providing a steady source of B. We continually refresh the B that was replenished such that B is always at a constant concentration. Okay? And so now what we get out of this thing, so our true second order rate would be K times A times B. So this would be our true second order reaction. Okay? But now, under pseudo first order conditions, this rate is going to be K prime times A. All right, so then I'll write next to that pseudo first order. And we recognize now that K prime, the pseudo first order rate constant, is going to equal the second order rate constant times the initial B concentration. Okay? So in other words, we absorb this B concentration into K, and we get a pseudo first order rate constant. Okay, so I'll say our pseudo first order rate constant is K prime with the appropriate units of 1/seconds, and our second order rate constant is this K right here. All right? And so now what happens under this scenario, okay, if I write now negative dA by dt equals K prime times A. So that's a differential equation that we can solve, right? No doubt. And hopefully you remember from the last discussion, solving the second order rate constant is much more difficult, although it can be done with a program such as Mathematica. But as far as fitting data, and you can see that I've got this data set that I had you fit earlier in the semester. I'm going to come up and talk about that in a moment. When we do pseudo first order, this makes fitting data and determining a rate constant much easier. So for example, when I go to solve this, I would come up with let me make some more room. Oops. So I'll write this under here. So I can say I'm going to put this in relative units. A of time t equals A0 equals now e to the negative k prime t. Okay? And so that would give us a nice exponential first order decay. All right? And what we also notice now is that in this relative units that I've got here, you can start to see this is how we're connecting this, right? If I plot this normalized concentration, then when I fit this an exponential like you did in e to the negative kt, the only fit parameter is the rate constant k. So now what about this x-axis? I didn't put this in time. It's called OH exposure, or just generally exposure. So what does all of that mean? Well, I'll remind you here. Let's expand on this. Okay, A at prime t over A0 equals E. So we said that K prime is K times this B. So let's fill that in. So let's actually go ahead and write this as K times B0 now times T. Okay, well, if we still want to fit this to an appropriate first order rate constant, then what we can actually do is, instead of plot this as concentration versus time, okay, instead we can plot this as relative concentration versus exposure. So what is exposure? Well, it's this B0 times T, right? So I'll say this little chunk right here, instead of time, it's what we call exposure. So in other words, it's the duration of time that a reactant is exposed to another reactant. And you notice it has units of seconds, molecules per cubic centimeter. And so that's because the concentration of B would be molecules per cubic centimeter times time in seconds. That gives us the seconds times molecules divided by cubic centimeters. Okay? And so now if I plot this x-axis in this way, okay, where instead of versus time, it's time multiplied by the concentration, then I will get a first order decay out of that. And when I fit this, I get an apparent first order rate constant. Okay? No, excuse me. I'm sorry. I misspoke there. I get the second order rate constant. Okay? Even though it's plotted as a first order, right? We remembered that K, not K prime, K is the true second order rate constant. So I can get the second order rate constant out of this thing by doing this in pseudo first order conditions and plotting it as concentration versus exposure. Okay? So I've run out of room on this slide.